The main focus of this video is going to be more Lenz's law practice, because I found that students just can't get enough Lenz's law practice. But I really want to start by bringing home exactly why this is so important and how power plants and generators use this concept of electromagnetic induction in order to power stuff. Okay, so we know that the equation for the EMF induced during electromagnetic induction is equal to negative the change in flux over time, right? And specifically, flux is B A cos theta, right? So remember, we can get an induced EMF, an induced current, anytime any one of these three variables changes, right? When we are talking about electromagnetic generators, almost always the variable that's changing is the theta, right? Because mechanical generators work in such a way that you have some mechanical object, either water, wind, steam, that turns a turbine, and that turning turbine changes the theta. Okay, so you can see in this picture here that I have that if you like rotate this crank in this picture, okay, you actually can see that this this little loop, it's kind of like a rectangular loop, is rotating, right? And that rotating loop between these two magnets, there's a north side here and a south side here. So that rotating loop is constantly having a change in flux because that angle is changing. The angle that the area is making with the magnetic field is constantly changing. That's going to induce a current in that little rectangular loop, and then off it goes to this little voltmeter where, you know, it starts measuring some voltage, right? Really, that voltmeter could be a light bulb in your house, all right? So how cool is that? That all you need to do is find some mechanical thing that turns either a magnet or a current-carrying loop, right, in a magnetic field, and that change in flux creates a voltage that then powers the entire planet. No joke, the entire planet, right? In the case of a wind turbine, it is wind that's turning this turbine, which turns the coil, which changes the flux through the magnetic field, which gives you a voltage. In the case of hydroelectric power, it is water that pours over a turbine, that turns a turbine, that changes the angle again of a coil inside of a magnetic field that induces a current in that coil, okay? And if you're talking about a nuclear power plant, you harness nuclear energy to boil water to create steam that turns a turbine, that changes this theta, that creates an induced EMF that gives you current for your home. That is how the world is powered, and now you are more powerful for knowing that. Okay? All right. From here, I want to look a little bit more at a few more Lenz's law problems. Okay? Just to give you more practice. So I'm going to start with another picture here of a magnetic field that is going away from you, like this, right? Okay? And inside that magnetic field, I have a current carrying, well, there's no current in it right now, but I have a loop of wire that may or may not have a current in it eventually, okay? It says, the circular loop of wire is in a uniform magnetic field. The magnetic field is directed into the plane of the figure, right? So, right? As far as your guys' perspective, it's this way, right? Determine the direction, clockwise or counterclockwise, of the induced current in the loop when the magnetic field is increasing. B, decreasing, and C, constant. Okay, let's get constant out of the way. We all know if this isn't changing, there's no change in flux, there's no induced EMF, there's no induced current. Okay, so C is obviously nothing, no induced current. Okay, but A and B are a little bit more interesting. All right, so let's suppose then that we suddenly have more magnetic field coming out this way. More magnetic field, right? It was used to this flux, right? Now I'm adding to it. more. Suddenly this loop's like, no, seriously, I don't want this more flux. I'm a boomer. Okay, so what does it do? Well, it says, I am going to create a current that opposes this flux, right? So it wants a new flux in, right? In other words, towards you, right? It wants a induced flux in this direction to cancel out this new flux in this direction. Well, what direction would give you that? Well, I need a magnetic flux in, right? That is, you can see from my thumb right now, that would be a current that would be clockwise. So you would end up having a clockwise current in that case. Okay? All right. Now, what if the magnetic field instead was decreasing? Well, since this is the opposite scenario, you can go ahead and probably guess that it's going to be counterclockwise. The induced current would be counterclockwise, but let's figure out why. Okay, now, once again, the loop is in this field. It is totally happy. It is enjoying life. But suddenly, you start taking that flux away. You take that B field away, right? And it panics. No! And it wants more B field coming this way like it was before, right? So you want more magnetic flux coming this way, right? What will do that? Well, if I want my magnetic field to come out like this, right? To wrap around and come out like this, right? That would mean I would want a current in this direction because that's the direction my thumb points in order to make that happen. All right? Okay, so that would be a counterclockwise current. All right. Lenz's law. It's not so bad. I hope this is helpful. I hope this isn't too hard with the learning glass situation. Okay? All right, we have another example. We're going to do one more, and then there's going to be one problem for you to practice on your own after that. Okay? All right. So in this third example, okay, it's kind of interesting. We have a wire carrying a current in this direction. Okay, and as you know, a current carrying wire will create a magnetic field, right, that will go in behind and come out this way, right? So this current here is going to be in here and then out this way, okay? So in other words, it'll be right? Do you see that? So in, out, okay? And so you have all these different loops around it, okay? This A loop here, and this, I'm going to put a little A, and it has a velocity going up. And there's like this little C loop over here, and there's like a little B loop over here, going this way, and there's going to be a little D loop over here going this way. Okay? All right. Now, the question is, will there be induced currents for moving these little loops in these various directions? Okay? The first question to ask yourself is, why would there be an induced current? Remember, induced currents only happen when there's a change in flux, and change in flux happens if the area is changing, the angle's changing, or the B field's changing. Are the areas of these loops changing? No, they're staying the same. They're like the same size loop every time, right? They're not being squeezed, expanded, anything like that, right? Is the angle changing? No, you're not rotating anything. Is the B field changing? Well, here's the thing. Remember that the formula is B equals mu 0 I over 2 pi r. That's the magnetic field due to a current carrying wire. So the bigger R gets, right? The bigger R gets, the farther away you are, right? As this gets bigger, B is going to get smaller. right? So in other words, the magnetic field gets smaller and smaller and smaller and smaller and smaller and smaller the farther away you are. Okay? And this magnetic field here on the bottom will also get smaller and smaller and smaller the farther away you are. Right? So as far as A is concerned, if I pull this little loop up, it's losing flux. It's losing flux going in this direction. Okay? It wants that flux back again. So if it's going to want more flux coming like this, just like in the last example, right? If we want more flux in this direction to make up for the fact that it's losing magnetic field as you pull it away, right? Then that means there will have to be a counterclockwise current induced in it to get more flux coming through this way. Okay? All right. That's the answer for part A. For part B, okay, we have a flux going this way this time, right? And as I pull it away, I'm losing flux going this way, right? I want more flux going this way to make up for the fact that I'm losing it by pulling it away. And so to have more flux in, right, I am going to want a current that goes like this and around. Okay? Right? So, okay, that will be a clockwise current. For part C, all right? For part C, I'm moving laterally. I'm not moving closer or farther away, right? So that means that the flux isn't changing, so there will not be any induced current in C. The B field it's staying at the same radius, so the B field is going to be the same. If B field doesn't change, there is no new flux, no changing flux, okay? All right, lastly, in the case of D, right, we're bringing it closer. In other words, this flux that's going in, right, is getting stronger and 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 stronger, right? It wants to create a flux that opposes that. It wants a magnetic flux coming out. In that case, it will induce a current that is counterclockwise, right? Right, so to get a flux coming out at you, inside there, out, you need a current up here, which corresponds to a counterclockwise current. Okay, which makes sense because it should be the opposite of what's happening over here in part B. All right, there's one more question that I have on Lenz's law that I want to save for your own version of practice. See if you get it. Honestly, this question should be Googleable, but if you get stuck, you can also reach out to Professor Google, that's me, and yeah, I have faith in you at this point. I have faith in you, after all this Lenz's law practice, that you will get the right answer. Good luck.